All right, can everybody hear me? Awesome. Okay. So last time we were here, we were talking about separable equation, and we end up with a example which is Friedmann's equation. Okay. I was naive to think like the last one is the case, and then it turns out it's not the case. So I went back and worked out all the details. This is what we got. Here we have the Friedmann's equation. The first thing is if k is small, the last term doesn't really matter. Okay. Second case is now we just need to focus on the formula of rho. For different formula of rho, we can solve for different A. Then we tend to say, okay, for matter, your A increase, your volume increase as A cube, then your density reduce as 1 over A cube. That's what we have for this case. We solve that, we have T equals to, A is equal to T to the 2/3, roughly those level. The second case we did was radiation. So if we have something like this, we have photons running around with the speed of light. As you increase the size, the number of photons reduce like this, but also the energy of the photon, because your wavelengths become bigger, your frequency become lower, also change as 1 over A. So together, rho is proportional to 1 over A to the 4th. We solve it. We find A is roughly T to the 1/2. Okay, the first two are correct. The third one, I said, the exponential part is correct, but the way I computed was wrong. So what we have for the third case is your rho is basically a constant. That's the third case. Okay, if it's a constant, you ignore the last term. Then what you got is basically A prime over A square is a constant. Therefore, A prime over A is a constant. Therefore, you have something which is exponential. So that explains everything. The key assumption here is rho is a constant. This constant, of course, is called the cosmological constant. It's the same term in Einstein's general relativity equation. Now we know it's corresponding to something called dark energy. Okay. As a result, your A is going to be roughly exponential. Sounds good? So that's the correction. Of course, this one is kind of weird. Basically means if you have a sphere, you increase the size of the sphere. If you have matters inside and you assume the matter doesn't change, then your volume become bigger, your density should be smaller. Make sense here? For fixed matter, your volume become bigger, your density should be smaller. However, for dark energy, it's different. You double the size of the ball, you double the matter inside. That means you are creating matter, actually energy, as you make the space larger. That's how you make a rho to be a constant. That's why at first, Einstein thought this is so counterintuitive. He thinks this is a mistake. Turns out this one is a constant, and that constant is not 0. So he later actually gave a correction of that. But either way, this is what we have for the last one, and so far, we know it's true. So together, we can have roughly the picture of how the universe expands. When it's hot, it's T to the 1/2. When it cools down, it's even faster than that. It's T to the 2/3. Finally, eventually, it's T to exponential. That's how our universe expands. Here's A, here's T. Like we said last time, we are right here. We are right at the edge that we started to grow exponentially. So eventually, we will be very, very far away from everything from us at the speed of exponential. Okay. All right, any questions before we move on? This time everything should be correct. Cool. 1.3, slope field. Okay, let's talk about slope field. Some people call it direct field. They mean the same thing. Okay. So we were talking about solve this. First order differential equation. I'm just going to say ordinary differential equation from now on, ODE. Differential equation. Okay. We know we can guess this. Now we know we can do it if it's separable. But what about in general? In general, it's hard to solve, but we do have a technique which can give us some hint. And this is the technique. This one tells you what? This one tells you if y equals 1, then y prime also equals 1. And if y prime equals 1, you basically know the slope of the curve there is 45 degrees. Okay? Therefore, what you can do is you can draw, and you put y equals 1 here. And then you can draw little tiny directions of the changing rate of your solution here, because it has to obey the differential equation. Similarly, for y equals 2, you know it's steeper with a slope of 2. Okay, I will draw one more line. It's pretty difficult to draw after this, but basically let's just say it's pretty extreme. Okay, after that, even if you cannot solve the equation, you do know if the solution is here, then the solution should go this way next. And then the solution hits here, the solution should go like that. You can actually roughly sketch the solution by tracing all the arrows. It's not accurate, but it's roughly gives you ideas. Make sense so far? This is called the slope field. Okay, so let me write it down in general. For first order, which looks like y prime equals a function of t and y, this automatically tells us, given a location, t and y, we know y prime. Y prime is actually a vector with a direction. So what we can do is we can draw y prime everywhere to get the slope field. This will tell us the trend of the solution. Okay. Now, next time, if you have something, you have some differential equation which you don't know how to solve, worst case, you could draw the slope field and try to guess, try to get a feeling what the solution looks like. Some side notes. Number one, when you draw the slope field, you are going to draw a lot of vectors. Every vector has two components. You have the direction, you have the magnitude, which is the size or length of the vector. Okay, so it's very possible if you start to draw arrows as the vector, at some place you have something really, really short. At somewhere you have something huge, like that. From here you can see it's really hard to see the trend if they have different length. Okay, so if you don't care about the magnitude, usually we normalize everything to make sure that all the vector has the same length. Okay, so all the arrows you're going to see, they all look nicely like this. They only give you the direction, but they don't tell you how fast or how long that thing moves. Usually this is what we do. Of course, if size means a lot, then you have to actually put the original magnitude there. Doug?
When we normalize the vector like that and set them all equal to like the same length, does that in a way kind of regularize the data for us? Or am I like, I guess I'm trying to think of like when you normalize it, it seems like
Okay.
there's less of an opportunity for there to be outliers or things like that, but I'm not sure if I'm thinking about it right.
Two things. Number one, you are talking about regularize, but I think the thing is called standardize or normalize, right? Standardize the data. Okay. The key you get here is you have your data, you take all your data, you shift to make the mean to be 0, and then you divide it by the standard deviation. In this way, you have the mean equals 0, and you have the standard deviation equals 1. That's called standardizing the data. Okay. A key here is, let's say you have 200 points. For every single point, you divide it by the same standard deviation. Because that's a feature of the data set, not for a particular sample point. Good so far? Now let's talk about standardizing, or let's say normalizing, the vector. The point is try to make vectors of different lengths to be exactly the same length. Can you see that for different vectors, which should divide by different magnitude? Not a single magnitude that works for every single vector. Your key is try to make everybody new unit length, not the whole data set has a standard deviation, which is 1. And the formula is given by, if we take the vector to be f, you simply just divide the f by its own length. After that, this whole thing will have a magnitude of 1. Do you see the difference? Cool. Yeah. Good question. All right, that's the first one. Second one. The book mentioned it. I thought I should mention here. There are 2 types of differential equations which are easier to draw. The first type, A, is something look like y prime equals ft. The second time is something called y prime equals fy. We call this autonomous. Okay. You know, in general, your y prime should be a function of both t and y. But if you have one of these cases, that means your direction field is easier to draw. For example, for A, if it only depends on t, doesn't depend on y, that means what? That means for the same t, you should have the same vector. That means all those vectors on the same vertical line should be parallel to each other because they share the same t. That's case 1. Case 2 basically means everybody on the horizontal line should share the same direction because you share the same y, and your derivative only depends on y, not x. For autonomous. Okay, so there's nothing special. Just for cases like this, it's easier to draw. In general, of course, if it depends on t and y, your thing can be anything. Every single one can be different. Okay, but these 2 are more uniform. Sounds good? It's actually very easy to see. For example, if you have y prime equals ft, that means something look like this. That means you can simply find the solution by just taking the integral and plus a c. Right? That means you can basically solve it, and your solution should be invariant under plus C. That means if your solution look like this, then you shift everything up by a same amount, which is plus C. They should still share the same shape, right? That means they should share the same vector field if you just move things up and down for T only case. Similarly, for Y only case, you just move things left and right. All your solutions should be parallel to each other. Okay? Is the idea clear? There's nothing more we want to talk about in this section. Let me show you some examples. Of course, we don't draw this by hand. Okay, y prime equals ky. We set the parameters. Let's do the thing. Now you can see all these are vector fields. The bigger the bigger the y prime. So technically the arrows should be longer when you move up, but I normalize everything, so now they look nice. Now what we can do is we start from a blue point, we track it down to the next point, and then we know the direction here, we track it down, we keep tracking it down. So if you put a lot of arrows together, you kind of see the trend of the solution. Okay. Now two more interesting things. The first one is, what if I change k? If I change k, I change the field. I can change it from a negative 0.1 to positive 0.1. The whole field, oh yeah, I have to make sure. Let's do negative 0.3. You can see it drops more dramatically, right? So the field start to change. Sounds good? Okay. But now if I change my k to be 0.1 and let it stay that way, how do I get the curve going this way? That means the field doesn't change, but I want to track a different track, a different trajectory. That is actually determined by your initial value. I started from 20. Because I started from 20, I need to track here, and then the next one will be here, and the next one will be here, and keep going. Make sense so far? But now if I want to start at 10, but keeping the field to be the same, that means keep the differential equation, just change the initial value. I should have the same field. I just start tracking different trajectories. Sounds good? So another way to say it is, if you know the vector field of a differential equation, you know all the general solution. But in order to figure out which trajectory do you want to track, because there are so many solutions here, you need the initial value. Once you know the initial value, the whole thing will be just one curve, not a field anymore. Sounds good? Cool. Now let's try some logistics. This is something we did before. We know how to solve it now, but let's just try. And you can see nicely, this is what's happening. You change something, you change n to be 20. You change the whole field. Okay. Now, if you want to keep the field to be the same, but you want to pick a different trajectory, you want to pick a trajectory which starts from 5 instead of 10, then what you need to do is just change your initial value to be 5, keep the vector field, and then you got a different trajectory and a different one. Sounds good? Cool. Similarly for this one, we can draw the same thing. The skydiving one. Even though we don't know how to solve it, but just by looking at this trajectory, at least you know somewhere you have a final horizontal asymptote, which means you eventually reach constant speed, even though you don't know what the solution is. Sounds good? Okay. Now if you take a look at what you have here, it's G minus K over M. Is there a t? No, there is only v. That means my velocity has only something to do with my v, but not my t. That means for the same v, but different t, I should have the same derivative. Now take a look at the direction field. For the same height, can you see all the derivatives are parallel to each other? Because it has nothing to do with your t, only your vertical height. Okay. Everything makes sense so far? You can go share the code online. So from now on, every time you see a new differential equation, probably the first thing you should do is just go ahead and try to plot it. Okay. See the vector field? You kind of see, wow, there is some like, I don't know, like a center there, something just spiraling in. Maybe there is a vertical asymptote. Maybe there is a horizontal asymptote. You can have those kind of properties right away by drawing this. Okay. That's what we have for direction field. So this section is over. Now let's talk about 1.4. I showed you several examples of how to solve this one using a computer. Let's share. It's time for us to talk about what's in the library. How do people solve it using a computer? Okay. And today we will talk about Euler's method. All right. What's there? Well, we kind of saw just now. Y prime equals ky, k equals -0.1. We kind of say, hey, we kind of draw the direction field, right? It's everywhere. Now what we do is, let's simulate what I did. We have this, and we start from y0. Let's just take it to be 200. That means at first I know I am at 0, 200. Because I am at 0, 200, I know y prime. Y prime is -20. That means the vector is going to be 1, -20, and then renormalized, something like that. Now what I'm going to do is I'm going to start from this one, go in this direction because that's where my function is changing, right? I am going to find my next point. Still okay? Now at this point, what happened? As long as you know a point, you will be able to draw the vector. That's what we mean by y prime. Still okay? Then tracking this, you go to this point. Then at there, you know another vector. And then follow this vector, go this much. By this, you draw it point by point, starting from the first one, and then second, third, and fourth. You track the whole trajectory, just as what we did in the graph just now. Make sense so far? That's what we will tell the computer to do. We just need to write it down to make sure it's formalized. And that is the Euler's method. Okay. What you have is, you have some dpq, first order. You have some initial condition. Let's just call it y0. Our job is to solve it numerically. Okay. Let's see how we do this. Okay. First, you know this is not going to be accurate because we cannot find it everywhere. We need to pick all the points we want to know. So from 0 all the way to t. We divide them into n intervals. They don't have to be the same, but let's make it the same for simplicity. Divide 0t into n intervals. For each step, delta t, we just name it to be h. That means we take equal intervals. You don't have to, okay? But we just do it. Then what we have is, we will know everything about t0 equal to 0. T1 equal to 0 plus h. T2 equals 2h, and all the way up to Tn equals capital T. Here your h is going to be the t divided by n. So we have all this. Okay. We know the first one. Now we want to do this, find the second one, do this, find the third one, and keep drawing, and move on. Still okay? Now let's assume we already know Tn and Yn. Tn we always know. Yn we have already computed. Now we want to go and find Yn plus 1. That means we find the next point. Okay, and how do we plan to do this? Now here's the point, Tn, Yn. Okay, here's the point which we're trying to find. And the way we are doing it is we are going to shoot a vector that way. This vector corresponds to y prime. So think about it. Y prime is nothing but y Tn, Yn. If you know Tn, Yn, you'll know this derivative. You know the derivative, you know the vector. The vector is going to be given by h 1 ftn yn. Now remember, you only want to move for h. Therefore, you need to normalize it to be this. Therefore, Yn plus 1 equals Yn plus this, which is h f Tn Yn. This is called Euler's method. Let's give it name Euler's forward method, because we do have a backwards. Okay, before we go ahead and give you the examples, any questions so far? Do you understand what I wrote here basically captures what we just want to do in this graph? Questions? Cool. So that's the Euler's method. From here, we can see if we know t0, y0, then we can compute y1. Once we know t1, y1, we can compute y2. We know t2, y2, we can compute y3. So this is a recursive formula. Write a for loop. This one will actually go forever, whichever you want. Okay. Now let's see an example. Let's take an easy one. Y prime equals 0.1 y. Y0 equals 1. Use forward Euler's method to compute y 0.2 with h equals 0.1. Okay. Tn, yn. Let's put everyone in. Yn plus h, which is 0.1, times f Tn yn. F is this. That is 0.1 yn. Together, it's 1.01 yn. Yn plus 1. Okay. We are looking for y 0.2. We start from 0 with step 1. Now we know we're basically looking for y2. We do 2 iterations, we get the point. Still okay? Now we just need to repeat this formula for twice. Y1 is 1.01, y0. Y0 is 1 by initial condition. Therefore, y1 is 1.01. Okay. Y2 is 1.01, y1. Y1, we just did it. Therefore, this one is going to be 1.01 square. Okay, whatever that number is. If you want y3, y4, y5, just keep going. Okay, sounds good? Cool. That's what we have for Euler's method. Should I show example now or let's see. Yeah, let's show it later. Or actually, let's show it now. Let's code it into a for loop. Okay. This is what we have from the Euler's method. So see all the blue points? Those are the Euler points I calculated using from 0 to 20, and I'm using 10 points. Okay, that means for each h is going to be 20 over 10, which give you 2. Okay, so every gap here between them is 2. The dashed line is the numerical one, and because for this one we know the true solution, therefore I put the true solution here. Now, several things you should observe. Number one, this one is pretty good. It captured the trend. Number two, this one is not the real solution. This one has some error. And you need to ask yourself, where does the error come from? Think about it. You take this point, you draw a vector, you follow that vector for this long, you follow another vector for this long. Every time you follow a vector, you basically follow a triangle. You basically assume that the whole thing from 0 to 2 to 2 to 4 is a straight line. But the original thing was never a straight line. Can you see that? Because of this is not a solution. This is actually approximation. Good so far? Okay. Now, if this is the approximation, how do you make the approximation better? The error is this thing locally is not a straight line. Well, you can take more points to make h smaller. And as long as it becomes smaller, if it's a smooth curve, it becomes more and more like a straight line. That is what we learned from calculus. So instead of 10 points, let's do 20 points. Our expectation is we're going to put more points here, and then the red dashed line is going to be closer to the green one because we took more points. Now you're more like a straight line now. And then we should expect if we take 50 points, it's going to be pretty good. And then if we want it better, we can take 500 points. And now you can see we roughly got the right idea, the right solution. Sounds good? Okay, so this is approximation, and to make it more accurate, just make more points. The more points you take, locally the curve is more likely a straight line. And if it's a straight line, it's going to work. This is coming from calculus. All right? That is Euler's method. And if you use your computer to solve this one by calling a function, this is actually part of the function. Okay, they're trying to run. Okay, I don't receive a lot of feedbacks here, so I don't know if you guys get it or not. I'm just going to rely on you guys to stop me. If you don't nod your head, you don't shake your head, you don't look confused, and don't raise your hand, I'm just going to assume everybody's okay. Okay, so I'll just keep going. Stop me if we need to go deeper in this. I don't know if this is easy or hard. All right, now let's see what we have here. Well, now we see. This is actually the first time you guys to do a numerical algorithm. That's called numerical approximation. Okay. From here, we can see number one, Euler's method is a numerical approximation. Is a approximation. Why? Because this is what Euler's method does. It goes from a straight line, it ends here. But the real curve may very likely to be this. So the real point is here. Okay, straight line. With this, a curve. Okay, that's why in general you have error. Now to make the error small, take smaller h. Then it's more like a straight line. We're going to have smaller error. From here, you can see more points means more memory. More points means more computation. So basically what you're trying to do is you're trying to throw in more resource to get a better result. That's good. Better results. Okay. This is the first thing we want to talk about. Second thing you should think about is this. If you do Euler's method for twice, you do this, and then you do this. Okay. Now, if you think about the real thing is a curve. For the first iteration, you already have an arrow. Your second one is actually based on the previous arrow plus another arrow because the second part is not straight either. Make sense so far? Therefore, the more points you take, the bigger the arrow. At the first, maybe the arrow is small, but if you do it for 10 steps, at the end of the 10 steps, it's going to be big. At the end of the 100 steps, it's going to be ridiculous. We call this accumulated arrow because every single step creates an additional arrow plus every arrow you had before. Okay. That means what? That means if you use the Euler's approximation to solve a function, to solve an equation, okay, its prediction here at 5 is going to be better than the prediction at 10. Because 10 is longer, you accumulate more error. Does it match your common sense? It's like it's harder and harder to predict what's coming later. It's easy to predict what's going to happen next hour. It's harder for next day. It's harder for next year, and so on. Okay. Good. That's something doable. Now here comes the interesting thing. Number 2. We know a smaller h is going to be better error. Okay? But a smaller h means more points, more resource. The question becomes, can I have a better arrow without adding more points? That would be fantastic. That means the second way is better than the Euler's method because you basically use the same resource, but somehow you have a better arrow. Sounds good? That goes to the design of the algorithm. That means if I have two algorithms, they have the same h, but somehow one is better than the other. That means the same resource, we have a better algorithm. And then we just keep developing better and better and better. In this way, we increase our computing power. Still okay? Now, how do you do that? I will give you some example. That's roughly something called error analysis. You need to know where the error comes from, which is the curve and straight line. Of course, there's an error, but this time, moreover, you want to quantify how big your error is. Quantify the error of Euler's method. That's the case. Okay. And then if you have another algorithm, you quantify that. You point out one is smaller than the other. You know which one is better. Now let's take a look. What are you trying to do? This is Euler. Okay. Now think about it. What you're trying to do is you can move this one to the other side. And then you can divide by h. Still okay here? What's that? That's the derivative. That's the difference quotient. What's on the right? On the right is ftn yn, but really what you have here is y prime. So the error fundamentally come from, you are basically taking a y prime and you say, hey, y prime equals limit h goes to 0, yn plus 1 minus yn divided by h. But now I cannot let h goes to 0. I just say, hey, let h equals 0.1. Let's calculate this. The error basically come from here. Your derivative is not your real derivative. It's approximation. Make sense so far? Okay. Now, can you quantify that? Can you quantify how much you're off by replacing your derivative by this? Of course, you're off. Okay. And here comes the interesting thing. Yn plus 1 is nothing but f tn plus 1. All right. And ftn plus 1 is nothing but f tn plus h. And ftn is nothing but yn. Good so far? Now let's take the Taylor expansion. Try to recall. If you don't recall, just as long as you feel this one looks familiar, that's fine. Factorial tn plus h minus tn plus f prime prime tn divided by 2 factorial tn plus h minus tn square and so on. Let's clean it a little bit. It's basically ftn plus f prime tn h plus f prime prime tn some constant times h square plus f prime 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 tn h cubed divided by some constant and so on. Still okay so far? Now what we can do is we can move this term on the other side. Combine them. Which is basically your yn plus 1. Minus yn equals f prime tn h plus f prime prime tn, okay, h square dot 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 dot, and finally if you divide it by h, we have the thing we want, h plus f prime prime tn times h. Originally there was a square, but now you divide. You plus something h square, we don't know what this thing is, plus something h cubed, and so on. Now it's clear where you get the error. You're basically trying to say, I'm going to use this one to replace this one. That's what you did before, right? Now can you see where the error is? The error is actually in every single term here. So several things. Number one, if h goes to 0, then there is no error. These two are the same. Because everybody with an h here will disappear. So that's a good news. Okay, but the second thing which become interesting, if h is 0.1, how big is your error? If h is 1, how big is your error? Now let's take a look. The error is basically absolute value of this one minus this one here, which is basically the absolute value of everything here. So f prime prime Tn h plus something h square plus something h cube, keep going forever. Now we need to use the arrow formula, which we really don't care. It's just something you copy from calculus 2. But a common sense should tell you when h is small. For example, h is going to be 0.1. What about h square? 0.01. What about h cube? 0.001, and so on. Can you see that all these arrows compared to the first one will be relatively small? Okay, then only the first term matter. It comes from arrow estimating, which is actually very similar to geometric series. But either way, roughly, we cannot say exactly the same, but roughly, it's the same level as a constant times h plus some very little tiny arrows, which we don't even care. That's when we say this one's big O, h, and that is the arrow of replacing this derivative by this difference quotient. Your arrow is OH. That means what? That means your arrow is at the level of h. That means if you reduce h by half, that means your arrow is going to be reduced by the same magnitude. Because your OH, h become 1/2, your arrow become 1/2. You make h 10 times smaller, your arrow become 10 times smaller. Sounds good? Cool. That's how we quantify the arrows. Now, what do you mean by you have a better algorithm? Later we can show there is another way of doing this derivative. That is OH square. That means what? That means if your h reduced by half, your arrow reduced by 4. That means your h become 1/10 as before, your arrow become 1/100 as before. So OH square is better than OH. OH cube is even better. OH fourth is even better, and keep going. Okay? So the whole thing about algorithm design is how to design the algorithm such that the error is reduced in this way. I can give you the formula. You can try to prove by yourself. Before we did this, right? And this one is roughly OH. There is an arrow. Now we have a better way of doing it. We do ftn plus h minus ftn minus h over h. This one is going to be OH squared. The proof, you can do it by yourself, is by Taylor polynomial, Taylor expansion. Some of the error terms cancel each other, so you have the next one. This one is called the center difference, central difference method. Okay, which is better than Euler because you have a smaller arrow with the same number of points. Okay, that's all for today, and let's continue on Wednesday. I will stay here for questions if you have any.